So our research is real-time change detection using synthetic aperture radar videos. Research team includes Dilan Dinushka, Dr. Adisha Vijayasiri and myself, and we are from University of Moratuva, Sri Lanka. So first let me introduce what this synthetic aperture radar is. Synthetic aperture radar is a kind of radar that the radar antenna is like hold on to a target region and it is moving in a aircraft or spacecraft. It can be any airborne moving platform. So why we call this is a synthetic aperture is regardless whether this aperture is actually physical or synthetic, this allows to create high resolution images compared to small physical antennas. So this is in cost wise, this is very cheap compared to other radars. So this is a sample video we took from Sandia National Laboratories, and you will see what the synthetic aperture radar video is. Here you can see that the vehicles are moving in. If you see my cursor, these are the vehicles and they are moving. And you can see that there is a particular axis in rotation in each image frame. That's because the antenna is mounted on an airborne vehicle and it is rotating around that region. So the motivation of our research is that we can use this in military applications for remote terrorist location identification, civilians, rescue missions, and search and tracking. Research objectives can be explained as follows. In order to detect changes in near real-time manner, we found out there were various major challenges. The first one is the image registration. Due to this issue of rotation of axis in the airborne vehicle, each image frame is subjected to a motion. So we need to correct this before going to change detection. And there is this dynamic background. And the speckle noise is inherent to any SAW image. So this noise need to be filtered before we go to the further processing steps. And finally, we have to detect the changes in near real-time manner. So the proposed solution approach is consists of 4 steps. First, we do the image rotation correction using various feature detection techniques, SURF, ORB, SIFT. And after defining the features, we calculate the homograph matrix to find out the matching points. And then to smoothen the transition effects of the image frames, we use a video stabilization technique. Unsharp masking, oxybinderization, histogram equalization were used for speckle noise filtering. And the algorithm that we developed for change detection comprise of two parts. The first one is we use this optical for calculation using Lucas-Carnade method, and we combined it with this blob detection and analysis. Finally, to improve our algorithm, we did possible parameter fine-tunings and improve the algorithm to reduce the time complexity. So the research is a 4-step process. We derive the SAW video, then we do the pre-processing to filter the noise, then rotation correction, detection and tracking, finally the output. So these are some consecutive image frames that we acquired from that video I showed you earlier. So in these red circles, you can see the moving cars. Since these SAW images are reconstructed using backscatter pulses, and these backscatter pulses are not uniform, the objects or their shapes are not very visible or clear in the frame. So we need to have reprocessing techniques. So this is the output of binderized and unsharp masked video frames. You can see that here. If you see my cursor, these are the moving vehicles that are like shown in the black color pixel clusters. And this is the result of Gaussian Burr plus histogram equalizations. So we combined both the filtering techniques into our approach. And the next step is the rotation correction. We used several feature extraction techniques, SIFT, SURB, and ORB. ORB gave the best features out of all 4. And then we used feature point matching using the normal Hamming distance. Finally, after selecting these points, we we used homograph metrics to calculate how similar the matching points in between two consecutive frames. So this is how these features were matched, and you see these are the two consecutive image frames in the video, and this is the result of the rotation correction. And finally, our final step of our approach is chain detection. So it consists of 3 steps. First, the optical flow calculation using Lucas-Carnot method, then blob analysis, then the combination of first 2 steps. Before going to our algorithm, let me explain the approach to what we did. So assume this square is an image frame, and we define a point distribution for each image frame. So these black color pixels denotes this pixel distribution. And for each pixel in the frame, we define a neighborhood n by n. So here you can see a 3 by 3 neighborhood for this red color pixel. So this is, we used a true threshold method for optical flow calculation. Assume that this x1, y1 is a pixel point in the pixel distribution of the current frame, and we can we can predict the location of that x1, y1 in the consecutive frame. That would be x2, y2, and that would be done using this optical flow calculation. So using these two equations, we can derive the apparent movement and the angle of deviation. So these two were used to detect the moving pixels out of the fixed pixels. So this is the first step of our algorithm. So this let T be this current frame. So this is the current frame. And assume there are n number of pixel points in the selected pixel distribution. And let this red pixel be the xk, yk. And this is its neighborhood. So for each I will explain that in the next slide. So for this xkyk pixel, we calculate the motion vector and the angle of deviation using the previous two equations, that is vk and theta k. And for the neighborhood also, for each pixel we calculate this motion vector and the angle of deviation, and we get the average value, that is v bar k and theta bar k. And we define two thresholds, k1 and k2, and we check whether this normalized value exceeds this k1 and k2 respectively. If that's so, then we mark this point as an interesting point. So what I meant by interesting point is that there is a possibility that this pixel would be moving. And for each entry in the pixel point array, we keep another entry in an array called counter array. So I will explain what this counter array will do. So if we found that the values of this pixel is exceeding both the thresholds, then we put that into the interesting point array, and correspondingly we initialize counter value and set it to 0. So the earlier steps I explained for the first initial frame, assume that the frame is not the initial frame. So this step is done to check whether any point that we mark interesting would be interesting in consecutive image frames. Assume that our frame is capital T, and we calculate the average sum of motion vectors from first frame to tth frame, that is v bar capital T. So in this equation, simple v bar t means the average sum of motion vectors of all the neighborhoods in a frame t. So we get the average sum from first frame to tth frame, that is v bar t. So the point that we want to check whether interesting is, let be pi, and its motion vector is vpi. So we do that normalization again and check whether that exceeds this threshold k1. If it is found exceeding, then we initialize its counter value back to 0. Otherwise, we increment the counter value by 1. Then we continue this process, and as we continue, if this counter value exceeds a particular threshold k3, then we remove it from the interesting point array. That means the point, even though we found a point is interesting in a particular frame, it is no longer getting consistent with the consecutive frames. So that way we filter out the interesting points. So these steps are continued in all the frames. And the next step of this approach is the blob detection. So why we do this blob detection is that there is no way of figuring out the actual physical characteristics of the objects. So these objects just represent as pixel clusters. So the blobs are the best way to find out these pixel clusters. Blob analysis have 4 steps. First, we do this grayscale conversion and do the image enhancements to adjust the image intensities. Then we define the thresholds for features of the blobs by area, by pixel intensity, by circularity. So in order to separate the static and dynamic blobs, we combine the LK method with blob detection. So whatever blob which have a moving velocity can be considered as a moving object. So this shows how the combined algorithm works. Assume that the current frame is T, and assume there are n blobs detected in this particular frame, and we want to check, and there is a point called XTYT in an interesting point array. We want to check whether that interesting point is included in one of the blobs. So for each blob in the frame, we define following. So this red pixel is the middle point of the arbitrary blob denoted by this red pixel. So, and the Rn is the radius of the blob. And we define a square that is Rn distance away from red pixel both vertically and horizontally. And we define An, that is the array of pixel points which are drawn within the square of this x and yn. So for each point in the square, we check whether that interesting point is found. If so, then we can mark that as a change. Otherwise, we increment by 1, we can consider the next block. So these steps are repeated for all the frames in the video. So this shows our algorithms. First algorithm is to derive interesting points, and the second algorithm is the combination of blob detection and optical fog calculation. So these are the results that we got after testing with the video. You can see that there are some green dots. These are the pixel distribution for the frame, and the blue dots shows the interesting changes. Since most of the moving objects, that means the vehicles, are on the rod, the majority of the distribution of blue pixels is around the rod. And this is the result of blob detection. You can see that here some red circles, those are marked as blobs. So you can see on the edge of the rod, there are blobs marked. Those are trees. So that's why we combine the optical flow calculation with blob detection to separate these static blobs and dynamic blobs. So this is the result of the phase 3. Here you can see the moving vehicles are detected. However, we got some false positives here. So we need to improve the algorithm. And these 2 frames we took from a SAW simulator video. And the moving vehicles are here also. You can see on the road there are moving vehicles and they were detected. And for the final results, we tested our algorithm with 4 videos, and there were some comparatively low falsely detected changes. Out of 49 changes, we were able to detect 42 correctly, and falsely 7 were detected likewise. So as further improvements, we hope to improve the efficiency using vectorization, and there is a possibility for using parallel computing, since there are many follow-ups and we can improve the performance. So we are trying to increase the accuracy of the change detection by defining methodologies to obtain better thresholds. So that's all from my side, and thank you very much for this opportunity. Thank you.